Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Starship is now flying and landing. How does SpaceX control a 15-story tall, 250,000-pound vehicle? Each of the Raptor engines has a mass of over 1,000 kilograms and a weight on Earth of over 10,000 newtons. How are they able to pivot so quickly? And how does SpaceX generate enough force to control them? And where did they develop the science that allows this control? All these important questions will be addressed in today's lesson. To accomplish this amazing feat required a tremendous amount of work behind the scenes at SpaceX. SpaceX does not order its most complex equipment from vendors. They will contract out simple pieces, but anything complicated, from the computers on, they construct in-house. There are several reasons to do this. Making sure your team understands every aspect of your ship is one of them. The other is maintaining a high standard. SpaceX lost a Falcon 9 rocket and payload in 2015 due to a poorly manufactured strut from a vendor. This is not uncommon in the aerospace industry. Some companies will cut corners to increase production, but these changes may compromise quality control. For these and other reasons, SpaceX designs their own engines, cryogenic tanks, avionics, guidance and control software, and ground support equipment. Let's look first at the Falcon 9, because this is where SpaceX learned almost everything that allows the Starship to fly. In the Falcon 9 User's Guide, we find that an analysis by the Aerospace Corporation proved that 91% of launch vehicle failures in the previous 2 decades were attributed to 3 causes: engine, avionics, and stage separation failures. A close analysis of how others have gone wrong can keep you from making the same mistake. The Falcon 9 uses the Merlin engine, which was the first new hydrocarbon-fueled engine in over 40 years. Special attention was paid to the turbopump system. Turbopumps are a common failure point in large rocket engines. For simplicity, the Merlin uses an open-cycle gas generator system, rather than the closed-cycle full-flow staged combustion system of the Raptor. Falcon 9 is a medium-sized rocket. It is mostly built of aluminum-lithium alloys, with some carbon fiber, steel, and Inconel components. SpaceX wanted to start out with something simple and reliable. With Starship, on the other hand, they are building the largest rocket ever launched. The Starship must squeeze every ounce of efficiency out of its Raptor engines. This requires a precise engine control system. The thrust-to-weight ratio of the Merlin is reported as 185. The thrust of the Merlin in vacuum is 981,000 newtons. If we divide 981,000 by 185, we get a weight of 5,303 newtons. Divide that by the force of gravity, 9.81 meters per second squared, and we get about 633 kilograms per Merlin. That means the Merlin is producing 1,550 newtons per kilogram. The Raptor has a maximum reported thrust of 2,210,000 newtons. The thrust-to-weight ratio of the Raptor is reported to be about 200. Dividing 2,210,000 by 200 gives us a weight of 11,050 newtons. Dividing the weight by the force of gravity, 9.81 meters per second squared, gives us a mass of 1,126 kilograms. Using these numbers, we can see that the Raptor produces 1,962 newtons of thrust per kilogram, making the Raptor 21% more powerful kilogram per kilogram. 9 Merlins are mounted under the Falcon 9 like this, while 6 Raptors, 3 vacuum and 3 sea level, will be mounted on the Starship like this. When these engines fire, the rocket must track the force produced in total and the performance status of each engine individually. If one starts to malfunction, it must be shut down. The other engines will not only have to increase power output, but also their thrust vector to compensate. A rocket engine's thrust is vectored through a vector control system. Let's do a deep dive into how the Falcon 9 and Merlin engine get the job done. Starship will be similar. Here we see a Falcon 9 schematic. This looks simple enough. Not really. Let's start by zooming into this simplified diagram of a Merlin's systems. Starting up here, we see connections for commands coming from and feedback going back to the onboard computer. Let's look at how this computer would start the Merlin engine. The onboard computer would send a start engine command to the engine control unit. The engine control unit will initiate a startup program. First, it will send a command for this valve to open. This is the high-pressure helium valve. When this valve is open, it allows high-pressure helium to flow from a carbon-overwrapped titanium pressure vessel through the high-pressure helium valve and into the turbopump. Helium has a lot of energy when it expands. Then the helium starts the turbopump spinning. When the turbopump RPM is sufficient, the engine control unit will then send a signal to the fuel control unit. The fuel control unit controls these 4 valves. The fuel control unit will send a signal up, commanding the opening of these low-pressure valves, which will allow liquid oxygen and RP1 to flow from their tanks. Both of these have been supercooled to increase density. These flow on into the turbopump. The pump is already spinning from the helium. This will allow oxygen to start to flow through the turbopump into these lines, and RP1 will flow into these fuel lines. This fuel line will send fuel through the thrust vector control valves and into the thrust vector control actuators. These valves will help control the movement of the Merlin engine when it needs to gimbal or reposition itself to change the thrust vector. The engines will be set to a neutral position to start. Here we see an electronic feedback loop between the TVC control valves module and the engine control unit. The fuel then flows up back around to the low pressure valve. The spinning turbopump increases the pressure of the propellants. These are not yet at high pressure, and the high pressure valves here will stay closed. The fuel will still be able to come down this line to the regenerative cooling heat exchanger. This is the cooling jacket over the combustion chamber and nozzle. The fuel starts to flow through this jacket and back out through this line, which brings the fluid up to the high pressure valve. These lines will carry some liquid oxygen off here, where it will also be stopped by the high pressure valve. An oxygen line can also be seen going this way, to this oxygen valve. Fuel is also sent through a line to a similar RP1 valve. When both these valves report sufficient pressure and flow here, the engine control unit commands both the LOX and RP1 valves to open. When both these valves are open, the fuel and oxygen goes into the gas generator. The gas generator has a spark igniter, like a spark plug. A sensor detects cold fuel and oxygen in the gas generator and reports this to the engine control unit. A command is then sent to the spark igniter. The spark igniter starts sending electrical arcs through the gas generator chamber, which starts the fuel and oxygen burning to produce hot gas. A sensor detects that the gas is burning and shuts off the spark igniter. The hot gas from the gas generator comes over through here and starts spinning the turbopump at high RPM. A sensor detects this, and a command is sent to turn off the high-pressure helium. Now the gas generator is spinning the turbopump. The turbopump comes up to full power and pressurizes these lines. When a sensor detects that the pressure is high enough in the propellant lines, a command is sent from the fuel control unit to open the high-pressure valve, allowing fuel and oxygen to flow through into the fuel trim valve. The fuel trim valve can make adjustments to the oxidizer fuel mass ratio. This unit senses the mix ratio and compares it to the programmed ratio. They may go oxygen-rich to start combustion. After adjustments are made, this valve opens. Fuel and oxygen are starting to flow through the fuel trim valve and into the combustion chamber. The combustion chamber is made of a superalloy called Inconel or Inconel. If you are unfamiliar with these alloys, watch this lesson. Back to the combustion chamber. The sensors know that the combustion chamber is cold as cold fuel and oxidizer flow into it. The fuel control unit will next send a command to open this valve. This is the TEA-TEB tank or TTEB tank. It holds triethyl aluminum and triethyl borane. These chemicals burn at an extremely high temperature on contact with oxygen. They also give off a green glow. That is why you might see a green flash when a Merlin rocket engine starts. TTEB flows into the combustion chamber and starts burning at a very high temperature on contact with the oxygen. Fuel and oxygen start to burn in the combustion chamber. This temperature and pressure sensing unit detects the rising heat and pressure and sends a signal to the engine control unit. The engine control unit sends a command to close the TTEB valve. Coming out of the turbopump here, we see the exhaust gas. This gas is routed through a heat exchanger to heat and expand cold helium, coming from the pressurized helium tanks. These tanks are again usually carbon-overwrapped titanium pressure vessels, or COTPVs. The heat exchanger heats and expands the helium. The hot expanded helium leaves the heat exchanger to go back and pressurize the propellant tanks. The gas generator exhaust continues out of the heat exchanger and into this roll control nozzle, where it is then vented overboard. The roll control nozzle acts like a reaction control thruster to help roll the rocket. That way, the propellant that goes through the gas generator not only powers the turbopump, but also helps control the rocket. This nozzle will be set to a neutral position. Here we see a roll control nozzle sensor to tell the computer what state the roll control nozzle is in. And here we see a roll control nozzle actuator to control the direction of the nozzle. But what are actuators? Quite often we want to send an electrical command to a device to move something. The Merlin engines have a mass of more than half a ton. How can we move them? The Falcon 9 rocket uses high-pressure RP-1 to move these engines, and to control the grid fins on the booster during landing. Remember that these grid fins can hold a small car, and a lot of power is needed. That's where hydraulics come in. Hydraulics is the science of using high-pressure fluids to move heavy loads. We saw high-pressure RP-1 come into this vector control valve and actuator system. By directing the flow of high-pressure fuel, the engineers of the Merlin engine are able to move valves and other parts of the engine. By varying the amount of high-pressure fluid that goes to the low-pressure valves, we can open or close these valves. Let's take a quick look at how this works. The company Galco created this immensely helpful video. Here you see different hydraulic components, and a worker manually opening a valve. Hydraulics can be used for fine movements, or hydraulic power can amplify a movement, giving it a lot of power to lift or crush. Here you see examples of hydraulic rams or actuators. Hydraulic fluid is controlled by the valves you see here. Now let's look at actuators. Here we see the components of a hydraulic cylinder. There is a tube to contain everything, two inlet outlet ports here and here, a cap with seals to allow the actuator arm to extend without losing the fluid, and a piston back here. When we direct the fluid flow in one direction, we extend the actuator arm. We can position the control valve neutral to keep the arm extended, or we can cross that flow to retract the arm. Again, moving the control valve to neutral to keep it retracted if we want, or open the valve to extend it again and hold it there. Now let's look at how an actuator system can be used to control a large high-pressure valve. Here we see a hydraulic actuator valve being assembled. And here is the actuator arm. Once all the seals are in place, we can place this actuator over a large butterfly valve. And put the valve in a pipe. We add our hydraulic lines, by controlling the flow of hydraulic fluid to the actuator, as you saw before, we can open this valve despite high pressure resistance. Once enough fluid has flowed through the pipe, we can reverse the hydraulic fluid flow going through these lines to close the valve. You will notice that this actuator has a stop screw adjustment and a mechanical locking mechanism to prevent it from opening accidentally. This is a beautiful example of a hydraulic actuator. Now back to our diagram. Now we have looked at almost every module on this diagram and followed every line except a few. Here we see a feedback loop between the onboard computer and the engine control unit, so the avionics in the rocket know what is going on and can send commands. Here we see a thrust vector control sensor. This sensor is receiving input from the engine on its current thrust angle and power. Here we see the combustion chamber exit, which would go through the throat into the nozzle and form this plume. We also see a line here, labeled TV actuator. These are the physical devices that move an engine, seen here. These are hydraulic actuators, and are powerful enough to move the heavy engine. The Merlin engine was the most effective, efficient, and powerful engine ever flown, until Raptor came along. Reviewing this diagram, and maybe drawing it out a few times, will definitely help you understand rocket engine control. That's enough for today. Don't forget to like and subscribe, and please help support us on Patreon if you can. Thank you for listening, and stay safe. At Astra Pro Terra.